Good afternoon, ladies and gentlemen. My name is Sven Ebschke. I'm from the TU Dortmund University in Germany, and I'm presenting today the results of my master's thesis with the title A Monocrystalline Absolute Pressure Sensor with a Pseudo-MOSFET Readout Device for Life Science Applications. First of all, I would like to give you an outline of my work, of my presentation, sorry. The first thing I would like to show you is what are absolute pressure sensors and what are the conventional readout mechanisms. Then I would like to show you our novel concept approach here, following by the mechanical analyzing using an FEM software. And then I would like to show you the fabrication process and our results. Finally, I would like to show you my summary and give you a short outlook. So, what are absolute pressure sensors? Basically, we have a sealed cavity here, and we create the absolute pressure inside. And we have two methods for fabricating them today. It's the bulk etching and the surface micromachining. In the bulk etching, we are etching from the back side of the wafer and creating our membrane here. With the surface micromachining, we are depositing new layers and using them for functional layers and sacrificial layers. For the readout today, we have the capacitive, piezoresistive, and piezoelectric methods. For the capacitive method, we are using two electrodes from both sides and measuring the distance change via the capacitance change if you apply pressure from the outside. With the resistors, we have to do some kind of a Wheatstone bridge here on top of the membrane for creating the readout. And for the piezoelectric readout, we're using the crystal structure of silicon. The problem here is we only have linear readout, and it's poor for life science applications. So we want to have much more higher sensitive devices. And therefore, we have a new novel, new concept approach here. We're using SOI, silicon on insulator substrate, for creating the cavity, and we want to create a Pseudo-MOSFET on top of this stack here, and we get a much higher sensitivity in the area of the channel here, of the MOSFET channel. And as I said, we are doing the whole readout then via this MOSFET. And it is full CMOS compatible then. So first of all, we did a model in ANSYS with a membrane thickness of 250 nanometers, and we did research on the aluminum and nitrate materials on top of it. And our dimensions here for the membrane are 16 times 16 micrometers, 20 times 20, and 24 times 24 micrometers. Yeah. So we found out that the critical factor here is the von Mises stress. And the maximum von Mises stress in aluminum is 170 MPa, and it's 35% of the maximum yield. So our conclusion here is that the maximum pressure we can apply is 11.4 bar at the membrane size of 16 times 16 micrometers square. Now I would like to show you the fabrication process of our device. So as I mentioned, our base substrate is the silicon insulator substrate. So we have the silicon bulk material, silicon dioxide in the middle, and as the top layer also monocrystalline silicon. First of all, we need a hard mask here in our process, wire thermal oxidation of silicon dioxide on top of it. Then we spin on some resist here, using e-beam lithography for creating nanoholes. And as you can see, we made a whole area of nanoholes here for creating our membrane area. Then we are etching the silicon dioxide, removing the resist, and we're using the silicon dioxide here as a hard mask to etch the silicon top layer. Afterwards, we are doing an HF step, or a buffered oxide etching step, of the silicon dioxide for under-etching these, or undercutting this membrane here. And you can see we're creating the cavity here below the monocrystalline silicon top layer. Afterwards, one of our approach was to seal this with plasma-enhanced chemical vapor deposition of nitride here. And you can see we get a sealed cavity here in this picture. This is the top view now. For creating our Pseudo-MOSFET readout device, we have to create, first of all, a kind of mesostructure here. Then we are removing the silicon top layer on this part here, etching some trenches for the connections of the drain and source on top of the membrane, evaporation, an aluminum layer on top of it, and then we are structuring the drain and the source contacts here. You can see we have the both connections here on top of the membrane of our device. In the end, we have to operate aluminum on the back side of the device for creating the backside gate contact here. And this is our final device then. We got the drain and the source connections here and the backside gate connection, and we have the MOSFET channel in our membrane area. So these are some results of sealing the cavity. This is done by thermal oxidation. So we did several approaches, as I mentioned before. This is one by thermal oxidation, and you can see that it is completely sealed here, but it's not, there is still some stress in the membrane. So it's not a perfect way for sealing it. And here you can see some pictures of the full device in the end, or the top of the full device in the end. So you have the drain in the source contact here, and you have the connections over the membrane area with the MOSFET channel in between. And it's 5 micrometers of length here. So these are the output characteristics of the Pseudo-MOSFET. So you can see a perfect ambipolar output characteristic. But we have really not such a high amount of output current here, so we need to include an amplifier in our next step. So now I would like to come to my summary. So we use silicon on insulator as base material, and the process here is full CMOS compatible. We're using EBL for creating the nanoholes. We did some approaches of sealing the nanoholes by a different method, as mentioned, by thermal oxidation and evaporation of nitride, and also of aluminum, and so on and so on. And we created a prototype with a Pseudo-MOSFET on top of it. And in theory, you can have a maximum pressure here of 11.4 bar. So what we have to do now is we have to find a suitable operation point, and we have to integrate a full CMOS circuit on top of the membrane. I mean, this is the main advantage here. We have a monocrystalline membrane, and we can now use it for creating full circuits on top of it. And also, for the perfect readout, we need an amplifier on top of it for amplifying this small current there. And of course, what we have to do now is to calibrate this device with a defined pressure. We didn't do that by now. And also, you can think about using this new technique and combine it with other sensors, for example, in 3D packaging or other things. And you can also, or we should also test it in real life science applications. This is it. Thank you for your kind attention.